acceleration is 9 inches per second square. And then we find the rotation acceleration, which is the tangential acceleration over radius of the gear D. The equation is 9 inches per second square over 3 inch. The normal acceleration is 3 radian per second square. Because the motion is uniform in its acceleration, we can use this equation. What is this called? Omega is velocity of rotational velocity equals to initial rotational velocity plus the rotational acceleration times t. And then we got the omega is 10 radian per second. The position in terms of rotation is equals to initial omega initial times time t plus 1/2 times rotational acceleration times t squared. We get the position is 14 radian. And then we try to find the number of revolution. Because the position of rotation is 2 pi radian, we can search the revolution by calculating this equation. It is what's it called? Theta rotational positions time 1 revolution over 2 pi radian. We get the number of revolution is about 2.23 revolution. The second question is we will going to try to find the velocity of mass B of the load B because of the pulling of point C. It is we get it by calculating this equation. The radius of the larger gear times the angular velocity. The angular velocity of the large gear is equals to angular velocity of point D, which is the same as 10 radian per second. We calculate this. The radius is the larger gear, which is 5 inch. We get 15 inch per second, which is the upward motion, because the gear is pulled the smaller gear is pulled to the right, and then the larger gear, because it is the same shaft, we get the larger gear also turning to the right. In turns, the load B will be pulled to the upward motion. The last question is, how do we get the acceleration of point D at time 0? First, we already get the tangential acceleration of point D, which is the same as point C acceleration. It is 9 inches per second. And then we try to find the normal acceleration, which is pointing to the center of the circle. We get it by calculating this equation. Radius of D, the small gear, times the angular velocity squared, which is 48 inches per second squared to the center of the circle. The total acceleration is this equation, the square root of tangential acceleration squared plus the normal acceleration squared. We get the number is 48.8 inches per second. And then we try to find the angle in which the acceleration is going, because the normal acceleration is pointing downwards to the center of the circle, and the tangential is pointing right to the right. We calculate the angle, which I use this angle, and then angle phi we try to find by using the equation tan phi. It is the normal acceleration over the tangential acceleration, 48 over 9, and then by using the inverse tangent, we get the angle V is 79.4. I think that's my answer, ma'am. Please correct me if I'm wrong.
Okay, thank you. First of all, it's kind of difficult to see your writing. Can you zoom it? I asked you in the beginning to zoom it so that we can see
Oh yeah.
what you have written. Okay, is there any questions? Okay, so my questions is so VD is equal to VC. Why is it VD is equal to VC?
Because the point D, I think it's because the point D is connected to the rope, the same rope as point C. The question states that the rope is pulled to the right at the acceleration 9 inch per square and the velocity of 12 inch per square. Because it is the same rope, the small gear is attached to the same rope, and then the point D and also point C is the same rope, and then the velocity and the acceleration is the same. I think that's the reason.
Okay, then now can you go down a bit? Okay. Answer for point A is clear. Yeah, it's clear. Omega is the omega initial plus alpha t. So theta. So this formula for point A, you mentioned in the beginning this formula applies only for uniform accelerations, right? So in this case, the accelerations, is there an acceleration here? Constant acceleration of 9 inch per second square. Okay, so uniform acceleration, so you can use this formula. Okay, and then number C, from point B to point C, it's a bit messy. So if you do your quiz, I will suggest you to make it tidier than this, okay, Farhan? Otherwise, if I read it wrong, I will consider it wrong. Okay, so point B, what is the questions for point B? Velocity and change in position of the load B. Okay, what is the velocity of B?
It's 50 inch per second upward.
You get it from 5 inch times 10 radians. Why is it 10 radians per second?
Because the angular velocity of the load B is the same as the angular I'll try to. The load B is attached to the gear at point here. Is the cursor clear or not? Visible or not? My cursor. Yeah. Yes. The load B is attached to the gear here at point here. Point E here. I call it E. The angular velocity of this gear is the same as angular velocity of this gear. So because the angular velocity is 10 radians per second, we get 10 radians per second times 5 inch.
Okay, so you get 50 inch per second. Okay. And then the last question says number C. AD equal to AC. Is D and C in the same rope?
Yes.
Okay.
D and C.
All right, and then the
This
last
is the
one.
tangential.
Okay, so you get the acceleration. The total acceleration is AG, the tangential, and the normal. And how do you get the tangential acceleration and the normal acceleration?
I get the tangential acceleration of point D. It is equal to the point C because it is the same rope. The normal acceleration, I get it by using this equation, are the radius of D, radius of gear D times the angular velocity of D square. It's the initial angular velocity.
Okay.
I think that's.
All right. Is there any questions from friends? No? If not, then thank you very much, Farhan Rabani. Now, question number 2, Fifi Bella Kalista.
Okay. Is it clear?
Yes, it's clear.
Okay. So for number 2, we need to determine the angular velocity of the gear and the velocity of the upper rack R and the point D of the gear. So first of all, we know that the velocity of the point A is 2.2 meter per second, and we know the radius for the inner and the outer. And then point C is in contact with the stationary lower rack, and we assume that that is the position of instantaneous center of rotation. So first of all, we need to draw the imaginary line that perpendicular to the velocity at each point, and the intersection of that imaginary line, we get the instantaneous center of location, and then we put it in another drawing and make it a little bit clearer. And we know that the radius A is 250 millimeters and 150 millimeters, and radius B is 250 millimeters. And then from this we can start count for the omega at point A. So the omega at point A is velocity of point A divided by RA, and then we get 8 radian per second. That's the answer for question A. And then for question B, we need to know the velocity at point B first. So we get the equation velocity at point B equals omega times radius at point B. And then we just count it and we get 2I meter per second. After that, we know that the velocity at point B equals the velocity of rack R, so it's same. So the velocity of rack R is 2 meter per second. And then after that, the velocity of point D, we must know the radius of D first. We search it with the law of sinus, and then we get the radius of D is 0.2121 meters. And then after that, we can know the velocity at point D equals omega times RD, and then we get the velocity of point D is 1.697 meter per second. And then after that, I just count the velocity components at X and Y axis, and from that we get the at the x-axis 1.2, y-axis 1.2. So the factor 1 is 1.2i plus 1.2j meter per second. And then I think it's all answer the question.
Okay. Is there any questions? Okay, let me see again from the top, and can you zoom it? It's too small for me to see. All right, so first you're trying to find velocity at point A. Omega is VA divided by RA. Why you are using VA divided by RA?
Because actually I want to search for the omega, not the velocity, like the title.
Yeah, no problem. My question is actually this. My question is omega equal to VA divided by RA. So why you use VA divided by RA to find omega?
I think because it is in the center of the pulley, so I think it's the angular that we search, angular velocity.
Okay, why not using another radius? This is my questions. Why you are using radius of A?
Because it is right in the middle of the pulley, I guess.
Okay. And the velocity at point B, how can you find velocity at point B here? VB equal to? Yeah, how do you get this velocity at point B? Can you explain again velocity at point B?
So the velocity of point B, I get it by omega of the pulley times with the RB. RB is the distance between point B with point I.
RB is, okay, so this is 250
millimeters, yeah.
Okay. And then the velocity at point B equals to the velocity of the rack A. Okay, this is tangential velocity, right? Yeah. Then next, velocity at point D. How can you find velocity at point D?
So the velocity at point D, first of all, I must know the RD first from the triangle. So I use the law of sinus with the angle. So I search it with RA equals sin 45 and RD equals sin 90, and then I get the RD. And then after I get the RD, I search it with the velocity at D equals omega times RD. So I get the velocity at D.
Okay, this is correct. Is there any questions? I think it's quite clear. It's quite easy because you got it already in the class of physics. Thank you very much, Vivi.
Okay, thank you, Miss.
Okay. The answers are all correct. I'm not sure if I have to explain it again. It's just for one. Just want to explain a bit for the last questions. For the last questions, you know, if you have a ground, then you have something rolling, not sliding. So I assume you know the difference between rolling and sliding. Gliding is more a synonym of rolling, I guess. Gliding. Okay, so this, if you have, let's say, and you have to differentiate between pulley and gear. Okay, You finished the class of drawings, engineering drawings, right? So you know the difference between pulley and gear. So don't mix it all together. They are totally different. So let's say if I have a ring or a gear or pulley or anything which can roll on the ground like this. So it means the center of rotation is no longer here at the center of, let's say this is pulley, at the center of the pulley, but the center of rotation now it is moved to this, the contact point here. This is what your friend called the instantaneous center. So we call this as a center of rotation. Because the center of rotation now is moved to the contact point here, then if I want to find the tangential velocity or acceleration or v at this point, v, let's say vb. So the way I find it is I draw a straight line to my center of rotation and perpendicular to my velocity. If I know the omega, the angular velocity, so my VB is simply my omega times this length. So let's call this RB. This is RB, okay? RB, this is correct. Now, find the velocity at this point, any point in the circumference. Circumference means the outer. So here is, so the velocity is not like this anymore, okay? So the velocity should be like the way your friend is drawing. You should find, you should draw the straight line like this to the contact point and take a line perpendicular to that dashed line. So this is V, let's call this VE, point E. All right, so how can you find velocity at point E? You just have to find this length. What is the length of RE? Times omega. So all omega, remember last week I told you omega for all points in the body, they are the same, the value are the same. Okay, so here we still have the same omega, but with different lengths times RE. All right, this is quite basic, but you have to remember this. All right, so this is quite clear. Now I will go a bit further for three-dimensional space. I will explain it myself. Let's go check the questions. So the questions for three-dimensional rigid body, I have given it in class 9, just below the meeting 9. Okay, and don't forget to click for the attendance. I'm sharing it again in the chat group in case for you who forget to click for the attendance today. Okay, let's see the questions for three-dimensional space. So here is for a three-dimensional space. Now we have a crane. I'm working with crane as well with my students. Now we have one crane as shown here. It rotates with a constant rate, omega 1, 0.25 radian per second, and then simultaneously. Simultaneously means at the same time. Okay, this is sophisticated words to use. So simultaneously means at the same time. The telescopic boom, what is telescopic? You know telescopic, right? So telescopic boom is being lower at the constant rate omega 2. So in three-dimensional space, you will have even 3 rotations. Now, we are living in three-dimensional space, okay? So your body is expanded in three-dimensional space. We are not living in two-dimensional space. So let's imagine we have X and Y and Z, and always draw the axis by using right hand rule. So if you draw X and Y, then the Z axis will not be pointing downward. This is wrong. This is left hand rule. We are all using right hand rule. Okay, so it means if you rotate like this to the right, you will produce Z axis upward. So this is right hand rule. Okay, now I will draw another thing. If I draw the X to this axis and Y to that direction, so what is the Z axis? The Z axis will still be pointing upward like this. Okay, but you cannot draw like this, X and Y and Z like this. This is completely wrong. Okay, this is wrong. So because if you rotate X and Y, always the rotation is starting from X to Y, and then Y to Z, and then come back Z to X. This is right hand rule. So if you rotate this drawing, let's check this. Why is it important? Because it will affect your computations. So let's check this. If you rotate X to Y, what is the resulted Z-axis? The resulted Z-axis is not upward, but it is going downward. Okay, this is right hand rule. Now let's come back here in three-dimensional space. Okay, in three-dimensional space, we have, in the beginning, I told you motions. You can divide motions into 2 types. Motions, so you can have rotations. And then you can have also translation, or we used to call it linear motions. Okay, and then in three-dimensional space, rotations can be about 3 different axes, and translation can also be about 3 different directions. Okay, now if I draw it here in my three-dimensional space here, so the rotation means I can have rotation about x-axis, I can have rotation about y-axis, right? Then I can also have a rotation about z-axis. Likewise, or the same for translations, I can also move about x direction, translate or linear. I can also walk to the y direction. I can also walk linearly about z directions. So in total, for three-dimensional space, the motion of rigid body, it can have 3 rotation, plus it can have 3 translation. This is what we call it as a degree of freedom. In the class of vibration, you may call it in Indonesia is derajat kebebasan, degree of freedom. Or in some books, we call it DOF. How many DOF? 3 DOF, 1 DOF, and so on. So if you move like this, a combination of all 3 rotations and 3 translations, it means your rigid body, anything, your machine, my robots, for example, it can have 6 degrees of freedom. Right? Now you understand the type of motions and the number of motions in 3-dimensional space. I will come back to this screen. So this screen, it has constant rate, omega 1. So omega 1 is here about y. So this is rotation. You know we have omega 1 about y-axis. And then at the same time, the telescoping boom is being lower at the constant rate omega 2. So this is omega 2 about x-axis. It means omega 2 is here, like this. So it has omega 2 about x-axis. Knowing that at the instant shown, the length of the boom is 20 feet. So at this instant or at this time, the length is 20 feet and is increasing at the constant rate u 1.5 feet per second. And it can it can be extended or retracted with velocity u. U is linear velocity 1.5 feet per second. The question is, find the acceleration, the total accelerations of point B. So there is no angular, there is no specific words here, angular or linear. So this is definitely the A linear total of point B at this point B. So you combine, it can rotate like this. It can also rotate about x-axis, and also it can translate with velocity u 1.5. So what is the total acceleration? Okay, so let's see. I'm gonna share it with whiteboard. Is there any questions? Nope, so far. Okay, so let's draw the coordinates. So we have x, we have y, and we have z. Okay, let me check again. So omega 1 is about y. I will call this omega y. It's a constant 0.25 radian per second square, and omega x is 0.4 radian per second, 0.4 radian per second square, and u is 1.5 feet per second, and the length is the length 20 feet, and the degree is 30 degree. The length is 20 feet, and the degree at this time, this is, we may call this theta. I will write with different color. Okay, so here is point B. This is point B. So theta is 30 degree. Now find the find the total accelerations of point B. So in three-dimensional space like this, the only thing we can do is by using vector product. Okay, for two-dimensional space, like before, it's probably quite easy, or this is probably quite easy if I have a ring, I know the center of rotation, then find the acceleration here. So you know for sure that the angular velocity is only about one axis. This is the only omega. But if you have the case like this in three-dimensional space, how can you finish this? You will need a vector product. Okay. All right, now let's start. And how can you define B in terms of vector? So you have to remember again the vector. So B, if I consider this as a point O, so OB, if you remember the vector of OB now in three-dimensional space. So OB, you have three components, X, Y, and Z. Okay, in the X component, how can you define B with respect to X? Actually, this is a bit, the coordinate is a bit funny, so I will change it, for example, like this. So I will change it to be, this is the x-axis, this is the y-axis, and this is the z-axis. So the omega 1 belongs to omega z. This is omega z. And this belongs to omega y. Omega y. Okay, then how can we define point B with respect to x-axis? This will be, what is the length from O to B? The length from O to B is L. So L cos theta, and we need another angle here. And you know what is the angle? So if you remember the sphere, I will try it here. So let's say I take any point in the space, like this. like this, right? So we have this angle, and at the same time, we also have this small angle. Okay, and the red one, we call it as a theta, and the blue one, we call it as a phi. Okay, we call this as a phi. Okay, in this case, for the crane, for the case of crane, phi is equal to 0. Okay. All right, and then for the y components, usually other than cos theta, you still need to have cos phi, but in this case 0. Okay, and for y component, you will have L dot still cos theta and sine phi. And the last one for z component is sine L sine theta, right? Because you have to project it here, you have to project it here. Okay, now let's check. If phi is equal to 0 for this case, we know that phi is equal to 0. So I have only L, the x component, and the z component. Okay, and here I have 0, and the last one is I have L sine theta. This is for this position, but we also notice that it has omega z, so it means it will rotate. At some point, it will rotate. It will not be p equal to 0 forever. Only at this instant, p equal to 0. But somehow it will rotate. So we have to derive, instead of deriving this with respect to time, we have to derive this with respect to time. Okay, so now let's derive DOB with respect to time. So how can we derive the factor form like this? Now let's see this one by one. This is easy, so don't worry. Let's see this. L, is L changing with respect to time? Yes. How do we know? Because it has velocity u. So this velocity, we call it u. So it means this is a partial derivative. You remember in the class of engineering mathematics 2, you got time derivative, partial derivative. Okay, so if L is changing with respect to time, so we derive L first with respect to time. Now it becomes U cos theta and then cos P. All right, and then plus, how about theta? Does it change with respect to time? Yes, it changes, becomes omega y. This is theta becomes omega y. This is phi become omega z. Okay, then it means I still have L. I still have, now cos theta, if you derive this with respect to time, it becomes theta dot, and then cos theta, it becomes what, minus sine theta, if I'm not mistaken, minus sine theta cos phi. Okay, and then plus last one. Does phi change with respect to time? Yes, it becomes omega z. So let's change this directly to be omega y. Omega y. Okay. Then it becomes omega z times L times cos theta times minus sine phi. Okay, this is the first one, and on the second is we have to derive this again with respect to time, and so on. So basically, we have to derive this twice so that we can get accelerations. So we have to derive again. So we have to derive again. I will write it down here. So d square b dt square. So basically we derive what we got here from velocity again with respect to time. So at this point, why cannot we derive this? Why cannot we derive this? Because this looks easy. And this looks real because phi equal to 0. No, because again, you will lose some terms. For example, here it doesn't have phi, but basically you have phi dot here. Basically you have omega z. So if you, from the beginning, you already neglect many things, you will lose many terms. Okay, now let's see, for example, if the question is what is the velocity in the x direction? Okay, so I will draw it again here so you can imagine in three-dimensional space. So here is point B. So what does my vector DOB by dt means? So DOB, so I can just simply say dB by dt is actually simply the velocity of B. And the velocity of B, we can decompose it into three axes, VB to x-axis, VB to y-axis, and VB in z-axis. Okay, and then if you draw it in three-dimensional space, so it's simply like this. So this is my VBX, this is my VX, this is my VY, this is my VZ, that's it. And if this is vector, okay? This is still vector. So now if the question is what is the total velocity? What is the total velocity of this, let's say VB in scalar? We just simply square root of VB x square, VB y square, and plus VB z square. That's it. And this is the resultant. You used to call it resultant. And what is the direction of the resultant? It depends on the value of, if you check it here, if you can draw a box like this, right? This is the box. So the velocity is from point B pointing to this. I'm not sure if you can see it. This is the resultant. Okay, and then how about for acceleration? The same. So acceleration, if you write it in the vector form, so you have d square b db, yep, dt square equal to a vector b, so a b in x coordinate, and then a b in y, a b in z. So what is the total acceleration of b? Is the resultant of point, not v, sorry, should be a, is the total of a bx square plus aby square plus abz square. Okay, so this is the resultant. Now, for example, if the question is find the velocity of b in the x directions, this is just an example. So what is vb in x direction? So you take only the first component here. And then how can you get this? We know that phi is equal to 0 from here. I will write it down here again. U cos theta cos phi, and then plus, this is still cos phi, and then omega y times L times minus sine theta cos phi, and then plus 0. Why 0? Because sine phi is equal to 0 is 0. Okay, so you can put it here, all the value, 1.5 cos theta, cos 50 degree, what is that? Square root of 3 divided by 2, is it? Yes. And then plus omega y 0.4 times L 20 minus, so this is minus sine theta is half is 1. Okay, so here is the velocity at velocity of b in the x-axis. If you are using the vector form like this, what is the advantage of using the vector form? There are many advantages. First, we don't care about plus minus, because immediately if it gives you a minus, it will just minus. So we don't really care is u minus, so we have to put minus in the beginning, and so on and so on. We don't really care about that. If the final results give you minus, then it means deceleration. If it gives you positive, then it is acceleration. Okay, from here, any questions?
Excuse me, Miss. I want to ask. When and earlier you changed the x, y, and z direction from the question. Is it okay that we don't need to change the b position too? I mean, in the question, b is in between z and y direction.
Yeah.
And in this solution, you draw it between x and z direction. Is it okay?
Yes, I change it because this form, because you have to derive the position. Well, actually, it's fine if you keep it just like in the questions, it's fine. But why did I change it in the beginning? Because you have to write the position first, like this. So you have to write the position. Even if you, let's check if this is Z. So this is Z. This is X and Y. Even if like this, it's okay. So it means you have to change the expression for the position of OB, O to B. So you have to change this. Okay?
So in the first condition and the second condition, the B is still there. I mean, is it okay if the B is still there? Is it make the direction change or not in X, Y, and Z direction?
So so B is still here, so B will be still here. We just changed the direction of the frame. We call this frame, the coordinate frame, okay? But if you want to keep the same as the questions, you can also do like that, but the position here will not be the same. You have to change it. Do you understand what I mean?
Yes, miss. Okay, thank you, miss.
But if you want to keep the same as the questions, you can. It's just here will be different. So any other questions? All right, so let's check about the second. The second will be also more or less the same. Please remember partial derivative. It means you have to derive one by one. It depends on which component between among L, theta, and phi change with respect to time. For example, if L doesn't change with respect to time, so this will go immediately this will go immediately 0. Okay. Then from here, again, if I want to get the acceleration from here, you derive this again with respect to time, partially derivative. All right, so is there any other questions? So let me check if I have another solution.